Hi everybody, we're starting a new module today. It's modulus 5, the last module of the course. And the first lesson we'll be covering is an introduction to mathematical modeling. So let's first read the specific objectives for this lesson. Students will understand that linear models are appropriate when the situation has a constant increase or decrease. Slope is the rate of change. The rate of change has unit and context. Different representations of linear model can be used interchangeably. Students will be able to label units on variables used in linear model, make a linear model when given data or information and context, make a graphical representation of linear model, make a table of values based on linear relationship, and identify and interpret the vertical intercept in context. So many of these might be familiar to you from your study of algebra in the past. So let's see how it is presented in this course. So we're going to look at the problem situation number 1, comparison between the flat rate and a commission on sales salary. For employees in the sales industry, compensation practices vary. Some companies only pay the employees a flat rate salary, while others pay only commission on sales. However, most companies that pay employees in commission on sales also pay out some flat rate salary. Edgar is a part-time student majoring in art. Recently, he was hired as a full-time salesperson in a store that sells pictures and other decorative wall art. Edgar will work in a department that sells large wall art. All items in this department range from $100 to $1,000 in price. The manager of the store lets Edgar choose between 2 different ways to get paid. Option number 1, commission on sales. A combination of a base salary of $200 per week plus 3% commission on each sale, and the flat rate option number 2 is to get $500 a week. Which payment option you think is better for Edgar? Explain your answer. So look at the context of this situation and then decide what would you choose. I'll give you a moment to write your answer in a few sentences. Alrighty. I am anticipating, based on my experience teaching this class and teaching this particular lesson, that many students go with the flat rate salary, and the reasons that I usually get from students is that the flat rate is better because it is more consistent. Like, you know for sure you're getting $500 a week no matter how much one sells. So it's safer, it's more consistent. So consistent, and then you know what to expect. However, some students might say commission and say, because look, the stuff that Edgar is selling is pretty expensive. So once you get that commission, his salary might become more than $500. Okay, so answers can vary. But what we'll try to do is we're going to take the information provided in this problem situation and build what we call models. All right, so look at this table right here, and on the left side, the first column, the x, we call this the independent variable, which is the amount of sales in dollars that Edgar sells, right? While the output of this is we're going to be looking at 2 different variables. One is C, which is going to be commission on sales, while the other one is F, a flat rate. Okay, so those 2 variables, what we call, they are dependent, because they depend on the amount of sales than the one would make. Well, first I want to ask you, looking at the flat rate description, all right, here's the description that we got, $500 a week. What would you write in this column for each entry? What would you put? We're talking about, by the way, a weekly salary, Okay, right here, it's weekly salary. So how much would he make for each of these entries? All right, I'll give you a moment. Well, here for the flat rate, it doesn't matter how much he sells, it will be $500. $500 for each of those entries. It doesn't matter what he sells, his salary will be $500. Okay. All right. Now, how about if we look at the commission salary? So let me remind you what the commission salary is. So he gets $200 a week. Okay, plus 3%, correct? 3% on sales. Alrighty, so let's go ahead and do calculations. So for zero, okay, for zero, he is selling what? So he sold $0. So he didn't sell any of the art paintings, any of the artwork. So how much should he get? I'll give you a moment. Well, based on the description, he will get $200. All right, and nothing, he didn't sell anything, so will not get any commissions. Alrighty. How about if you sell $400 worth of artwork? How much would that be? I'll give you a moment to compute this. All right, let's check. So it's going to be $200 plus 3% on sales. Here we go. $200 plus 3% on sales. So that would be $120. 120. And then 200 plus 120 will give you 320. Okay, so $320. Okay, excellent. Alrighty, how about $8,000? How much would he make? I'll give you a moment. Okay, so let's review. So it's $200 plus 3% on 8,000. So that will give him $200 plus additional $240 in commission. So it's $480. Okay, so hopefully you get the idea. So I'll give you a moment to fill this all out, and in a second you'll get all of the entries on your screen. Alrighty, so now you see all the entries: 200, 320, 480, 560, 680, and 800. Alright, so now we are building a model. So based on the pattern of the computation that you have done, can you write an equation that will give us the cost of, not the cost, but the salary, commission salary, if X is the amount of sales that he makes in a week? All right, so for each of these calculations, you did the same thing. What did you do? All right, all of them had the same components. All right, so can you write the equation? I'll give you a moment to do so. Alrighty, so let's review. For each of the calculation, you had $200, correct? And then you added on what? 3%, and you multiplied by the sales. Here it goes. This is what we call a model. It's an equation that describes the situation for us. Okay, now so far we look at the situation that we had and we describe it verbally. It was given to us verbally. Then we describe it using table of values. Then we wrote the equation that relates things together, right? And by the way, all of these are interchangeable. You can actually go any direction. You can be given an equation, you can fill out the table, you can give a verbal description and write the equation directly. All of these are very much interconnected, and that's the feature of a mathematical model. Model is a description of a situation, and when you're modeling in mathematics, you're describing something in various ways. All right, so verbal, table, and equation. So when I ask you, what is another way that you can describe a mathematical model other than verbal table equation. What is the other way? Okay, I'll give you a moment to see if you can come up with one other way. All right, so the other way that you can also describe a model is by making a graph. All right, to describe visually what's going on. All right, and that's the other piece that we'll cover in this lesson. Now, by the way, there's part B right here that's asking him to write the equation for the flat rate. Well, the flat rate salary is just $500. By the way, it is still an equation. An equation is a mathematical relation that has two sides that you make equal to each other. So f equals to 500 is a mathematical equation which will also attempt to graph. So that's what is asked on this part. Now, if you're able to get a paper and print, not print, but the sort of do it by hand, I encourage that you do so. One thing is that what I would like to do is I would like to set this up. So we got the horizontal axis. The horizontal axis represents the sales. This is a general, it's an X variable. It's a general way to graph is where you put the dependent variable. So the dependent variable, independent variable goes in the horizontal. Like the amount of sales is considered to be independent variable. It's varies week by week, but once you know how much sales he gets, we are able to find the salary right here in dollars. All right. Now we need to decide how we're going to split this if we're doing this by hand. So now look at that scale. So the sales that he's making is, so we would like to display this data right here. You see? So it goes from 0 to 20,000. All right. So we want to display that in this region. All right. So we need to count how many boxes are here, and then you need to find a good estimate for what each partition should be. I'll give you a moment to figure this out. How much should each partition be? All right, so there are about 25 partitions, rectangles, and you have about $20,000 to split. So that gives you $800 for each box, but you can make it $1,000 because we're estimating. So I'll put right here $1,000 and then $2,000 and so on. Notice I decided to put in thousands of dollars instead of writing all those zeros. So it goes 1,000, 2,000, 3,000, and so on. All right, now his salary, remember, ranged from $200 all the way to $800. So now look at the scale and decide a nice partition that could be used for each of those dashes, just to make this appear neatly and so it fits the entire grid. I'll give you a moment to decide that. All right, so it's also 25 cells, so you have about $800 divided by 25. $800 divided by 25, so that gives you about $32 for each one. But again, we don't have to fit it way like that. Like you can go a little higher, because if you go a little higher, you can fill out more. So you can either go by maybe $40 or $50. That would be sufficient. Going by 100 would be too squeezed together, right? So I'll go by 40 just to make it as neat as I can. All right. Alrighty, so look at this. I went by 40s and got all the way to 1,000. So now we can go ahead and graph the data set. Alright, so we're going to go ahead and graph that data. So we got 200, 320, and so on. So at 0, he is making $200. So we're going to plot that point. Then he says 0 artwork. Alright, now when he sells $4,000 of artwork is 320. 4,000 is 320. So 4,000, and then I go up to 320. All right, then he get 8,000. He sells 440, I think. 8,000 is 440. Oh, it's 480. Okay. Okay, so let's take a look at the model that we got. So we have a commission equation, and we have also a flat rate equation. There's something that we need to outline when it comes to linear models. So a graph of a linear model is a line, and I would like to discuss a couple of characteristics of this. So take a look at this equation. So what this equation has that will be common with the other models is the way it is changing as you move. So as you can see, in this case, the more hours you work, of course, the higher is your commission salary. But that increase is not just random. What happens if you take a look at some of these points? For example, going from this point to this point, your salary goes $120 up for every $4,000 in sales. All right, so the more sales you make, the higher is your commission. But the rate at which the salary is increasing is constant. All right, so as you can see, it goes up $120 for every $4,000 that you that Edgar sells in the artwork, and that relationship is constant, so it creates that staircase. So I would like to write this over here where it says what are the characteristics. So one of those characteristics is a constant rate of change. Constant rate of change. And in this case, it is basically, what is it, $120 for every $4,000 increase in sales. Increase in sales. All right. Now, I would like for you to take this fraction and simplify it. Let's see what you get. Okay, so we can reduce to 0. So for every $400 increase in sales, you get 12 extra dollars. We can continue reducing this, and something interesting will happen. So we can take 12 over 400 and continue reducing it. Let's divide everything by 4, and then we get $3 increase in sales for every additional $100 worth of sale. Does that look surprising? That fraction, 3 over 100? Let's express it as a decimal. As a decimal, it is 0.03. All right, dollars in increase in salary for every additional dollar sold of artwork. Now, if you look at this number and you look at the equation that we obtained earlier, right here, notice that that actually appears already. It appeared in the equation description of a linear model, and it also appeared in the verbal description of the model, where it says that Edgar will be getting 3% commission. 3%, 0.03, and it also appeared geometrically when we calculated that constant rate of change. So this is one of the most fundamental properties of a linear model. Every linear model has a constant rate of increase or decrease. All right, so let me ask you a question. What is the constant rate of change for this model, for the flat rate? What would that be? I'll give you a moment. All right, so in this case, the constant rate of change here is actually 0. His salary would not grow at all for, doesn't matter how many sales he makes, so that one has a horizontal rate of change. Okay, now you might already look at this and say, oh, I've seen this before. And yes, you're right, you have seen this before, not in this class yet, but in your study of geometry. The constant rate of change in geometry is called a slope. All right, so that constant rate of change that we define right here is also called slope. We'll revisit this more in the next equation, in the next section, in the next chapter. So we talk about the slope a little more, but for now, just see that the examples that are presented in this lesson both are examples of linear models, and they both have a constant rate of change. All right, another thing that this model has is, if you look at the picture, is this right here. You see the $200 for the commission and the $500 for the flat. This is what we call a starting value, starting or the initial value. Okay, and I want to write this as a characteristic. So one characteristic is a constant rate of change, and the second one is that there is an initial value or starting value. So basically, if he sells $0 worth of artwork, which is our X, then his salary, commission salary, is going to be $200. All right, if you write that as a point, we write it like this: 0, 200. This is also called geometrically a vertical intercept. Vertical intercept. The vertical intercept mathematically is the place where your graph crosses the vertical axes. So the vertical axis right here is this. This is vertical. And this is where it's crossing. Theoretically speaking, that line can go this way. It could. However, we don't go to the left side because it is outside of the context of this question. We cannot have negative sales. So therefore, this will be our starting value. In application questions, I like to call the initial value a starting value because it helps us to understand how the model works. And now to summarize all of this, okay, for this particular scenario of the commission work, we can write that a linear model here, right, has the following characteristic. So the commission is the starting value, starting, all right, and then it is plus the rate multiplied by the sales, and the sales is the variable. So this is the variable, this is the variable, and the starting value and the rate are particular numbers that are characteristic of that model. So if we put that in equation, which we already did it before, but now we have the names for these things. So $200 is the starting value, and the rate is 3 cents for every dollar, additional dollar sold of the artwork, multiplied by the amount being sold. All right, so it has that relationship. Now, if you guys are already making connection to this, my props to you, because that's exactly where we're going. That M is the number in front of X. That's a constant rate of change of the slope. And a B is the vertical of the Y-intercept, which is the starting value. Okay, so hopefully it's kind of starting to look familiar. And now to make this look even better, we're going to look at another example of something that we are very familiar in New York City, and that's a Metro card. All right, so we know when it comes to Metro card, there are two options. There is an unlimited card, which is either the 7-day or 30-day unlimited card. The cost, and that's the those numbers are accurate for the year 2021. So it's $33 for the 7-day and $127 for 30-day unlimited card. And the regular Metro cards, each ride costs 275 cents, $2.75 with no additional bonus. It used to be that you get a 5% bonus prior to 2019 when you put a certain amount on your Metro card. It's no longer the case, so you pay for what you use. So $2.75 per each ride. All right, and then you know that if you get a new card, you have to you pay one additional dollar fee for the new card. All right, so we have another person where we're going to be looking at a particular situation. His name is Francisco, and he usually buys an unlimited Metro card each month. However, his friend Manjula says that he doesn't take the subway enough to justify the cost of unlimited Metro card. Francisco, so that's information, let's highlight it. Francisco takes the subway to work and back each weekday. He also takes the bus out to visit his parents every Sunday. All right, so that's his travel information. And we want to decide whether it makes sense for him to buy the unlimited card. And the way we're going to do this, one way to decide it, is we're going to look at the paper ride Metro card, the regular Metro card, and we will do the following. Question 1. Without using a calculator, estimate the balance on the pay per ride Metro card if Francisco deposit $127 to it. So in other words, instead of spending the money on the unlimited card, he puts all of that money on a regular Metro card and see if it would last him that entire month. Okay, so just quickly, what do you think? Will it last? All right, let's do a quick estimation. I'll give you a moment. All right, guys, so I'm not sure what you did. I mean, you might have even grabbed a calculator. Doesn't matter. It's just that, just to get an idea of what's going on. So whatever it is, if you figure it out, the total cost, I mean, you have to know how many times is he going to take a subway. So, each weekday, so that's 5 full weeks about, so 20, and then 4 Sundays, so it's 24 times 2, so maybe 48 rides or so, and then you multiply by $2.75 and see whether it will last him. It looks like he will be overpaying, right, if he using a regular Metro card. So you get an idea. We live in New York City, so we understand how it works. Now, we brought this example to build a model, basically. Just using this as a model so you can look at some situation that around us and understand that that idea of a linear model appears pretty often. So we're going to use a calculator, all right? So we're going to go ahead and just say, okay, what's the initial balance? So we start off with $127, correct? And then it says number of rides. All right, so if we do not use a card at all, so we start with the initial balance, they ask us to do R, probably for the remaining balance. We can just go ahead and say, okay, 127. You take one ride, your balance goes down by 275, right? You take another one, it's every time you swipe, it's basically decreased by $2.75. So let's grab our calculator and just let's fill out this short table. Okay, I'll give you a moment. All right, so now of course it's here. It's pretty straightforward what's going on, right? So you just take away $2.75 every time he swipes the card. All right, so this relationship right here has this characteristic that we're looking for. There's this constant rate of decrease that's going on, you see? So now if we try to write the equation for this, right? So think about this. It says R is the amount that remaining after each ride, and I'll help you out a little bit. Let's use the letter N for the number of rides. All right, so if N is the number of rides and R is the balance, and your starting value, you start with 127, then how would the equation look like? So we understand verbally what's going on. You have 127 balance. Every time you swipe a card, it's going to go down, the balance will go down by $2.75. How do you write it mathematically? I'll give you a moment. All right, so the remaining balance right here is the starting value, and then every time you swipe, you lose 275. So 275 times N. So if it's 5 rides, it's minus $10 and something, or $12. If it's 10 rides, it will be $27.50 that the balance will go down, right? So in other words, you first multiply by how many rides you take, and then you take it away from the balance. Our assumption that we start with 127 because we just want to see how the balance is going to go each ride. Okay, so now once we have this, we can go ahead and fill out this table. So we can just plug it in. So that would be 127. This will be 127 minus 275 times 5. This one will be 127 minus 275 times 10. The common mistake that students make with this model is that you're not subtracting 5 additional rides from what the balance is before, which you could, of course. You can just keep subtracting, but you see when you're jumping, you know, from 5 to 10, from 10 to 15, from 15 to 20, it's inconvenient to just go and subtract 275 each time. You just begin with the starting balance and you subtract the amount of rides that you make. You see, but it's from 127 from the initial one. You see, all of these are saying, okay, if you had 50 rides, what would your balance be? Okay, so let me fill out the first two, and then the rest I'll give you a moment to fill out yourself. So 275 times 5, that's $13.75. The multiplication we do first, right? So it's 127 minus 5 rides will cost you $13.75. So that will make our balance $113.25. If it's 10 rides, it will be 127 take away 27.50. All right, so it's 127 minus 27.50. That would be $99.50, and so on. So you first multiply by the number of rides, and then you subtract it from 127. Okay. Alrighty. So now in a moment, you're going to see all of this table filled out. Alrighty, so check this out. You could see that by 50th ride, the Mecha card is running out of money. Alrighty, so the minus balance means there was not enough to swipe. So here you got the relationship. Now, one thing that you again can notice is that as you go between equal increments, let's say you see between 72 and 44.50, 72 take away 44.50, the balance went down $27.50. The same thing happened here, $27.50. All right, while here the balance went down by how much? $13.25. This one is $13.25. You might say, so where's that constant rate of change? Well, because you see the rides that we're making is different here. So here, for every 10 ride, the decrease is $27.50. But look, $27.50 decrease for every 10 rides still gives you $2.75 per ride. So it's not going to violate the property that each ride costs $2.75. The same thing with 13.25. If you divide it by 5 rides, that will also give you the same answer. I think I made a little error. That's 75, not 25. 75, 75, 75. So that also will give you $2.75. So my point is that in this table, the way things decrease is consistent. All right. So graphing this, our lesson is getting a little bit too long. So what I want to show you is how to graph that same data on Excel. Alrighty. So let me show you. You can do it by hand. It's just there are sometimes Excel is going to be convenient. So I'm going to grab these two rides, and I'm gonna go by increments of 5 until we reach 50 rides. Okay, I'm gonna put the balance as being $127, and then I'm going to subtract $2.75 per every ride that I'm making. You see what I'm doing? I'm entering that same equation inside the Excel formula. Okay, and then what I'll do, I'll just double tap here, and it will fill out all of this information. And that's exactly what we got in the lesson, right? So as you could see, for every number, it basically used the starting balance and it subtracts 275 multiplied for every ride. On an Excel, the convenient part is that I can take this table and I can insert the graph. So here it goes. I'm just going to change the layout, so it's going to look a little pretty, and it also gives us the equation. So here it goes. Let's see if I can copy this into OneNote. Here we go. So actually this is convenient. I can just stick this in somewhere here. All right, it's asking us to describe the relationship. So this is going to be good enough, right? So let me zoom this out this way. Okay. I can actually have the space right here, so you can clearly see what's going on. All right, so you can also graph it by hand. Notice that Excel automatically does the horizontal axis as the number of rides, and then it uses the vertical axis as the, so this is the balance. This is the little R that we use, and the horizontal axis we have number of rides, which is N, and the equation using the variables that we have is the starting balance minus 275 for every ride. Now notice, you see again, this is what we call a constant rate of change. All right, so take a note on that. That's $2.75 every ride, and it also has a starting value, which is 127. So that's another example of a linear model. I think that concludes our lesson. So one thing that this also has, there's one more thing, which is you see the place. So basically, you see this is a vertical intercept, or the starting value. We write it like this: 0 rides, balance is $127. This is the rate of change. It's $2.75 for every ride. And there's one other thing that this one has, which is this value right here. This is called a horizontal intercept. What do you think the horizontal intercept means in the context of that question? What does it represent? When the graph crosses the horizontal axis, which is the balance, what does that mean? I'll give you a moment. Okay, so the place where the graph crosses the horizontal axis, it's when the balance become $0. All right, now if the balance equals to 0, we can visually see that it happens somewhere between 40 and 50, maybe like a little more than 45, maybe 46 rides. So if we go ahead and use this equation to try to find what that exactly equals to, we can actually do this. We've done this at the end of the other chapter. We can set this equal to 0, remember, like a blood alcohol content, and then we can solve for N. All right, so 275. And that, guys, something that you already done earlier. Remember, you have $127 on the card. How many rides will it last? You just divide it by 2.75 and you will get it, right? You don't need all this math to kind of logically understand what that represents. So 127 divided by 275 is 127 divided by 2.75 gives us 46.18. Well, 0.18 is decimal. We're talking about the rides, how many rides you can get. So it looks like there are 46 rides that you could take when the balance is still higher than 0. All right, and on the 47th ride, you're not going to have enough money. So will it last Francisco for the entire time? Well, it doesn't look like it, because he travels for every weekday. So that's 40 rides. Well, actually, it says there are about 22 weekdays in a month on average. So 22 weekdays, so that's 44 rides. And then 4 Sundays, that's additional 8 rides. So that would be 52. So he needs 52 or maybe 50 to 52 rides, depending on a month. But this card with 127 on it will only last 46. So it does make sense for him to buy the unlimited, given his, the amount of time he takes the train and the bus. Alrighty, now look, it's just an introduction to a linear model. We'll do another linear model next lesson. So we'll review those concepts. All right, and on that, I'm going to finish the lesson.